Hello, I welcome you all in this presentation related with the subject failure analysis and prevention. And we are talking about the general procedure of the failure analysis, and under this heading now we will be taking up the metallography of the failed component, metallography of failed component. Metallography is a very wide word which involves the various aspects like microstructure study. This we basically try to carry out with the help of the optical microscopy or scanning electron microscopy. Thereafter, identification of the phases, because microstructure study will be involving the phase and the grain structure study. So, type of the phases, relative amount of the phases and their distribution. Similarly, in the grain structure study, the size, shape, size of the grains, shape of the grains and their distribution. For phase analysis, we need to carry out the XRD analysis. So, this is another aspect we will be taking up it separately, which helps to identify the phases present in the metal. Then image analysis is carried out. Image analysis is carried out basically for 2-3 purposes, like the average grain size. This is one aspect, and the distribution of the grains also can be obtained. Similarly, the shape of the grains can also be identified through the image analysis, wherein factors like aspect ratio or the shape factor, which is like length to width ratio, is used to quantify the shape of the grains. Like for the circular grains, the shape factor will be 1, and in the needle shaped grains the shape factor will be very high, like say 5 to 10 it can be like. So, this is the length and this is the width. So, the length to width ratio gives us the idea about the shape of the grains. Then it also helps in determining the percentage fraction of the different phases which are there, and in addition to that the distribution of the phases is also identified. So, these are the various aspects related with the metallography. So, when we will be carrying it out, it helps us to identify or determine the number of important aspects related with the material which has failed. So, as far as the purpose of the metallography is concerned, it will help in determining the first the class of the metal which has failed. Like the class is identified if it is having the desired features or what kind of undesirable features are there. So, in terms of the desired features, like the fine grain size, equexed grain structure, this is what we want, but things actually may not be of the same type. There can be undesirable features in form of the inclusions, micro pores or the cracks. There can be segregation or there can be bending. So, these are the metallurgical defects which can be identified through the microscopy or metallography only. So, whether the desired features are there or whether they are undesirable features are also present. So, that will help to identify the class of the metal, whether it is of the premium quality, free from the impurities, defects, undesirable gases and the kind of the grain structure and the grain shape it has. Then estimation, another one is the estimation of the composition, estimation of the chemical composition. So, for the simple uh, metallic components, like for the simple metal systems and alloys, the composition can be estimated using the respective phase diagrams with the help of lever rule, with the help of lever rule. So, if we understand, if we determine the approximate fraction or the percentage of the different phases which are present, different phases which are present in the given metal, then using these percentage of the phases we can determine the we can estimate the composition of the metal system. This is particularly used in case of the steel. So, we will take up one typical example to understand this, like in case of the steels. We have the phase diagram of this kind, where this is corresponding to say eutectoid point, where we have the 100% perlite, and this is corresponding to the 0.05% of the carbon, where we assume that the ferrite, this side we have alpha iron or the ferrite, and between these two, if we have the steel of particular composition where the fraction of the ferrite is say 70% ferrite and 80 and 30% is perlite. So, using these fractions we can determine the chemical composition of the simple carbon steel. For this, what we use, the one side, this is the fulcrum of the lever, and this is the location of the 0.8% and this is the location of the 0.05%. So, in the lever what we have, the fulcrum F 0.8%, 0.8% and 0.05%, and this corresponds to the 70% of the ferrite in this particular example and 30% of the perlite. So, we can take up any phase to determine this one, so that carbon content in the steel can be obtained. Next is to determine the effect of the service conditions. When the component is exposed to the service conditions, it experiences the load, it experiences the environment, and it also experiences the the deformation. So, in some of the conditions, if the surface layer deformation is taking place, then there will be work hardening. Environment may be there, like enrichment or the loss of alloying elements can take place. Sometimes due to the high temperature, the precipitation of the undesirable constituents in form of say like the chromium carbide or there can be formation of the iron nitride. So, these will be embrittling the metal system. So, iron nitride will be embrittling the steel, increasing the hardness, while the chromium carbide formation will be leading to the loss of corrosion resistance, especially the intergranular corrosion takes place if the chromium carbide precipitation is occurring. So, metallography helps to identify whether there has been a loss of alloying elements or enrichment of the alloying elements, and these losses or enrichments will be leading to the change in structure, which will indicate the possibility of the change in chemical composition. Similarly, the deformed grain structure near the surface layer will indicate the possibility of the work hardening or the formation of the undesirable precipitates at the high temperature in form of the chromium carbide iron nitride, will also indicate the possibility of the change in mechanical properties. Then method of manufacturing can also be identified through the metallography. For example, if the dendritic structure is observed in the failed component, that will suggest that component has been formed by the casting, or if the grains are elongated in one particular direction, then it will indicate that it has been produced by the bulk deformation processes. Then the heat treatment of the component, if it has taken place, then heat treatment was designed as or heat treatment was imparted at the stage of manufacturing, or it has been accidentally exposed to the higher temperature conditions which has modified its structure. So, based on the background history of the failed component and the service conditions of the failed component, we can identify through the structural modification through the microstructure study if it has been really subjected during the manufacturing stage, or it has been exposed to the temperature during the service. So, this possibility of the structural modification due to the high temperature exposure can be identified through the collection of the background information or the service conditions. It will indicate whether the heat treatment was designed or heat treatment has occurred accidentally, and because of which the metallographic changes in the component have taken place. Then other conditions if are experienced by the component, like oxidation, corrosion and the work hardening, these also can be identified through the metallography in terms of the kind of the microstructural damage or the oxidation presence of the oxides, or the deformation of the grains near the surface layers will help to identify that if the work hardening has taken place onto the component. Then metallography is also helpful in identifying the characteristics of the cracks and the way by which it has been propagating, whether the crack is transgranular, means it is moving irrespective of the grains and the grain boundaries in a particular direction, or it is following a particular path, whether it is that path is following a particular grain boundary or particular kind of the micro constituents. So, the characteristics of the cracks can also be identified or studied through the metallography, and that also can help us in identifying the way by which crack is propagating during the fracture. Then what were the factors responsible for nucleation and the growth? Especially this point is especially important for the fracture initiation point. So, metallography of the initiation point is also done with the very great care to identify what are the factors which have contributed towards the nucleation and their growth, and for that we try to look for if some kind of the defects in form of inclusions or pores are present, or some particular kind of the microstructural defect is present in form of the bending, which has led to the softening and weakening of the metal, and because of which the crack has nucleated at that particular location. So, for the metallography we need one sample, and a sample need to be collected from the failed component. As far as the collection of the sample is concerned, there is no fixed rule, but it is normally sample is normally collected from the location from the fracture surface location. Because the fracture surface is also large, so especially we try to focus near the fracture through the macrofactography. If we are able to identify the fracture initiation point, then near the fracture initiation point the sample is collected normally from this location. This will help us to identify why the crack has nucleated, what kind of weakness in the component was present, because of which fracture has been triggered from that particular location. So, the sample is normally collected from the location where from the fracture has initiated. Another general thing which is kept in mind in collection of the sample is like if the sample is very big, then the sample is collected in such a way that it represents the entire mass of the component which has failed. So, a representative, a location representative of the failed component. So, this is another thing which is kept in mind while selecting the sample, and if the component has failed from a particular point, to identify that if in that zone only there was some problem or other areas were good. So, basically we also try to collect the sample from another location which has not failed. This is one thing, or we can take another new component for the comparison purpose, or another unfailed component which has experienced a similar kind of the service conditions. Sometimes if it is of our interest to study the path of fracture, then definitely the sample is collected from the fracture surface, especially where cracks are present, especially where secondary cracks are present. So, like this is the fracture surface and some of the cracks are present here like this on the fracture surface, then we need to collect the samples in such a way that the crack tip and crack tip can be studied to see how it was propagating, and such kind of the studies definitely are of the specific and are of more importance, especially in the fatigue fracture, especially in the region where crack has nucleated, to identify if there was some kind of defect or some kind of decarburization has taken place, or some kind of inclusions or the pores were present, and which have led to the nucleation of the crack to cause the fracture of the component. So, the fracture initiation point definitely becomes of the importance in the failure analysis for the for the metallography. So, whenever we collect the sample and metallography is carried out, what is the target of the metallography and what we try to observe. So, basically the first thing, as I have said, that we try to study the microstructure of the component, failed component, wherein phase structure and grain structure will be studied. We will also try to see if there is any structural variation. Sometimes we find that structure at the center is different from the surface. So, that will indicate the possibility of the segregation of certain alloying elements, or if some loss of the carbon from the steel component has taken place and which has led to the decarburization of the component. Similarly, opposite is also possible. If the steel component is working in the carbon rich environment at a high temperature, then it can pick up the carbon, and which can also change the microstructure and mechanical properties. So, the carbon pickup, decarburization, segregation, microstructural variation, if it has taken place due to the service conditions, then that can be studied. It can also indicate the possibility of the heat treatment, like if the component was subjected to the annealing, but annealing of the steel has been carried out, but actually it is showing the very refined grain structure, indicating the normalizing, or if it is indicating the martensitic transformation due to the quenching. So, that will indicate the possibility of the incorrect heat treatment which has been applied. Microstructure study can also help us to identify if there has been damage in the component due to the intergranular corrosion attack or the martensitic transformation. So, these are the some of the things which can be done as per the need, and now we will be seeing some of the microstructural aspects. Like this diagram shows that one structure is different from other, one structure is finer than other, and we can, through the image analysis, we can easily identify what is the average size of the white constituents. This is basically cellular structure with the eutectic matrix which is dark, and cellular grains are light etched, and we can determine the fraction and the size of the cellular grains while the matrix is the dark. So, the image analysis, it can be a very useful tool to identify the average size of the grain, shape of the grain, and the relative amount of the different phases which are present. And that is why once the microstructure is captured of the component, image analysis provides the much better information about the microstructural aspects. As I said, that the compositional estimation through the metallography is also possible, wherein we try to determine the fraction of the ferrite and the perlite. So, these dark phases at the boundary of the light etched ferrite is indicating the perlite, and the fraction of perlite is very less, and this is corresponding to the 1010 steel, which is indicating that it is having very low carbon, that is 0.1% carbon. So, it is a plain carbon steel, and another one is 1040 steel, which is indicating that there is a 0.4% carbon. So, obviously in 0.1% carbon, perlite fraction is very limited. So, this is what can be determined. We can easily, through the image analysis, we can identify what is the fraction of perlite, and then using lever rule we can easily determine the we can estimate the composition of the carbon content of the carbon in the steel. And this is 1040 steel having much higher fraction of the perlite, indicating the higher carbon content in the steel. As we can see, the segregation here in this particular case, like say this is the case of the piston, where we can see the made of the tool steel. What it shows that the failed component at the center has the different morphology than at the surface, and if we measure the hardness from the center to the surface, then what it will indicate that at the center hardness is very less as compared to that at the surface, which is being shown through the help with the help of these increasing size of the indent. So, presence of certain localized presence of certain element or absence of certain element in particular region leads to the variation in mechanical properties of the component. Similarly, this shows the bended structure, where which is indicating that the ferrite bends and the perlite bends are present. So, such kind of the variations lead to the lot of heterogeneity and variation in mechanical properties, and which under unfavorable conditions of the loading easily facilitate the nucleation and the growth of crack. Here this is another example of the segregation, which is leading to the presence of the undesirable constituents at a particular location, which are facilitating the nucleation and then nucleation of the crack and then the fracture. In case when the surface of the component is subjected to the external deformation due to the when the surface of the component is subjected to the surface layer deformation due to the external loading, or component surface is subject to the deformation during the manufacturing itself. So, in this particular case, what we can see, a drilled hole is having very deformed grain structure near the surface, and this is of about like say 20 to 30 micrometer. So, very deformed grain structure can be seen at the surface of the hole, and the hardness variation of the surface of the hole also indicates that the surface has been deformed. So, not just the hardness variation indicates the deformation, means work hardening due to the deformation, but the microstructural study also indicates that surface has been badly deformed due to the abusive grinding, or this is the typical nature of the machining process also, where surface layers are deformed. In the case when the steel component is exposed to the higher temperature conditions, then sometimes the loss of the carbon from the surface leads to the presence of the excess ferrite at the surface, which is soft, and this is termed as the decarburization. So, the loss of carbon from the surface is known as decarburization, and such kind of the losses reduces the hardness and the strength of the metal. Sometimes such kind of the variation reduces the yield strength of the material and facilitate the failure of the component. In opposite manner also, if the steel component is exposed to the high carbon rich environment, then that will indicate that carburization of the component has taken place, and overheating will be indicated through the coarsening of the grains. For example, at one particular location, this is the tube, and this location and this location here, if the failure has taken place from this location, then sample collection from this location will indicate that at the high temperature this zone has been subjected to the coarsening of the grains, or if excessive coarsening and prolonged high temperature exposure can also lead to the spheroidization of the steel component. This is the kind of problem especially observed in case of the boilers. So, if we compare, if the failure has occurred from this place, then we will take the sample from the two locations, one where from failure has occurred, another where failure has not occurred. So, this location may show us very fine and equexed grain structure as compared to the coarse grains. So, the excessive means high temperature exposure can also be a possibility of accidentally high exposure, accidental exposure to the high temperature conditions can be identified through the variation in the grain structure, which will be indicated through the coarsening of the grain. So, apart from the carburizing in carbon rich environment, a structural modification in terms of the coarsening can occur at a high temperature. Similarly, the soundness of the components can also be identified through the presence of some voids or the pores, if these are present in the steel. So, that will indicate if these have what quality of the metal was and if they have contributed in failure of the component. So, these are the various things that we observe during the microstructure studies to the phase structure and grain structure, and systematically image analysis help us in identifying the things with better clarity about the various aspects related to the microstructure. Image analysis of one particular weld joint, here what it shows, the dark spots are indicating the porosity, and image analysis and when image analysis is carried out, all these dark spots are selected and their fraction can be identified. So, not just the soundness, not just the microstructure study, the area fraction, average grain size can be identified through the image analysis, but it also can help in identifying the crack length or the fraction of the porosity if it is present in the component. Like this component which has failed due to the stress corrosion cracking, what it shows that grain boundaries have been completely eaten out. So, if the failure of the weld is taking place in the corrosive environment, especially of the corrosive sensitive environment, it means the corrosion sensitive metal exposed to that particular kind of environment, then the grain boundaries are eaten out and that will be causing the intergranular fracture, especially in case of the AISI 304 steel which is exposed to the nitric acid environment. So, the eating of the grain boundaries can be simply seen that there is a gap between the grains which have been created. Now, the microstructure sometimes facilitate the crack nucleation and growth is easily, especially when the grain structure is of the needler shape, tip of the needles provide easy site for the crack nucleation and their growth. So, needler structures are more sensitive for crack nucleation and growth than the spheroidal or spherical shape grain structures. Likewise, this is the another aluminum silicon hypereutectoid aluminum silicon structure where coarse polyhedral shape particles are present along with the needler structures. So, such a kind of the blocky particles as well as the needle shape constituents facilitate the easy nucleation and the growth of crack. So, if these are present, these may provide the easy site for the nucleation and growth of crack. In like semi solid processed aluminum alloys show the non-dendritic structure, and when such kind of the structures are subjected to the heat treatment, we find that at the grain boundary it is having very fine precipitates. It is more difficult to nucleate the crack whether it is grain boundary or within the grain if the precipitates are fine and they are spherical. So, it is more difficult to have the crack nucleation and their growth in such fine the precipitates as compared to the such kind of the needler constituents. So, it is always favorable to have the fine spherical constituents as compared to the needler shape. So, this is the another one where the needler shape constituents are present at the grain boundary, and it will be easy for crack to grow along the grain boundaries in such a kind of the cases. This is the another structure which is showing that the particular kind of the grain is in one layer, then another grain is another layer. So, such kind of the grains where the bends of particular phases are present, which is termed as the banded structure. Here the ferrite layers are present continuously. So, this is not considered to be a good structure where the one type of phase is present all along the length. It will easily provide the location or a path for the growth of the crack in a particular direction. If such kind of the bended structure is present, it is always there a structure. It is always good to have this structure, equaxial structure, where the proper distribution of the ferritic and the perlitic structure is present, phases are present in the steel rather than having the bended structure. So, now I will conclude this presentation. In this presentation, basically I have talked about the importance of the metallography and how can we do the metallography, and what is the importance of the metallography in the failure analysis. Thank you for your attention.